Hello everyone, welcome back to section 6.6 Calculus in Probability Part 2. In this video, I'm going to talk about cumulative distribution function, CDF. Cumulative distribution functions show how the probability accumulated as the value of the continuous random variable increases. And the formula for the CDF is capital F of t equal to the probability of x less than or equal to t is also equal to the improper integral from negative infinity to t of f of x dx. For f of x is the probability density function and x is the continuous random variable. In this formula, I used the variable t to avoid confusions with the random variable x of the probability density function. So basically, CDF is capital F of t equal to the probability of x less than or equal to t. Let's say t equal to 1, then f of 1 equal to probability of x less than or equal to 1. To understand this in more details, let's go back to section 6.4 where we talk about PDFs. We know that the probability of x between a and b is equal to the definite integral from a to b of the probability density function. Now assume that we don't have the lower limit of integration a. We just have the interval from negative infinity to b. So therefore the probability of x less than or equal to b is equal to the improper integral from negative infinity to b of f of x dx. Now let's apply this into a particular example to help us understand a little bit more. Let's consider this example. You have a normal distributions and f of x is the probability density function. For mu, the mean is equal to 0 and sigma, the standard deviation, is equal to 1. Using this normal distributions, I want to calculate the probability of x less than or equal to negative 2. This means that the probability is equal to the area of the regions underneath the curve from negative infinity to negative 2. So that means the probability of x less than or equal to negative 2 is equal to the proper integral from negative infinity to negative 2 of f of x dx. Let's increase the random variable x. Instead of calculate the probability of x less than or equal to negative 2, we can calculate the probability of x less than or equal to negative 1. So you can see you have a bigger region, so therefore the value of the area will be bigger as well. We're going to use the same formula. That means probability of x less than or equal to negative 1 is equal to the integral from negative infinity to negative 1 of f of x dx. And you're going to have a very similar setup when you calculate the probability of x less than or equal to 0, or you want to calculate the probability of x less than or equal to 1. Now let's go back to the formula of CDF. You have f of t is equal to the probability of x less than or equal to t. So whatever you calculate for the probability of x less than or equal to negative 2, or the area of the regions right here, that is equal to the capital F of negative 2. Or here, the area of the regions is equal to the probability of x less than or equal to negative 1, equal to capital F of negative 1. This regions right here, the area is equal to capital F of 0, and the area of this region is capital F of 1. At the end of the day, what you need to know when you're trying to find the form of CDF using the probability density function is that capital F of t is the area of the region underneath the curve from negative infinity up to a value t. This is once again capital F of t equal to the probability of x less than or equal to t equal to the integral from negative infinity to t of the probability density function. A few more properties that you need to know when you calculate CDF. That the left-hand behavior is always equal to 0, corresponding to impossible events. The right-hand behavior is always equal to 1, corresponding to sure events. The CDF is never decreasing. It's either increasing or flat. and the CDF is the antiderivative of the PDF. Now this is the end of the summary of cumulative distribution functions. Now let's take a look at a few examples on how to find the form of CDFs. Please let me know if you have any questions.